In this lesson, we're going to ask a profound question. Do they exist? And by they, we mean other life forms in our galaxy. And specifically, we're going to focus on the possibility for other intelligent life forms, intelligent civilizations. Now, we're going to put a requirement on these other civilizations. They must be able to communicate across the vast distances of the Milky Way galaxy. So we're going to try to estimate how many communicating civilizations might there be in our galaxy. And we're going to follow the work of Frank Drake, considered to be the father of SETI, the Search for Extraterrestrial Intelligence. And he's going to introduce an equation to help us estimate this number. Here is the Drake equation. N would be the number of communicating civilizations in our galaxy. And there are these terms here, and we're going to put numerical values in for these terms. And when you multiply these values and the units of each term cancel, we're going to get a final number. And that number will be an estimate of the number of communicating civilizations in our galaxy. The first term in the Drake equation is R star, the rate of star formation in the galaxy. Of course, we've learned that stars are formed from the gravitational compression of clouds of hydrogen gas, and then it gets hot enough for fusion to start. Of course, the most familiar star to us is our sun. And recently, on the 8th of April, in 2024, we had a solar eclipse, a total solar eclipse. So here's the moon passing in front of the sun. Here's the moment of totality. It's a beautiful spectacle. There's a solar prominence there. And more recently, on May 12th, we had a lot of people in the United States able to witness the northern lights, the aurora borealis, and this was due to heightened solar activity on the surface of the sun. You can see some really big sunspots down there. So these coronal mass ejections send high-energy particles out into space, and if they are heading towards the Earth, they interact with the Earth's magnetic field, and then these high-energy particles collide with gases in our atmosphere, and that excites the gases, and they emit different colors of light. But let's get back to star formation. Here's a picture of our Milky Way galaxy, and our galaxy has hundreds of billions of stars. And so what the first term in the Drake equation is about is the rate of new star formation. How many stars, new stars, are produced in our galaxy each year? Now, new stars tend to be produced in what we call nebulae. So here we see some of these red patches here, and even the dark areas here of the dust in the Milky Way here. These are nebulae, and a nice example of a nebula is the Orion Nebula. Here we see the Orion Nebula, and the red regions here, this is hydrogen gas emitting that color of light. So here we see a nebula that has the material, some more hydrogen gas to make new stars. The next term in the Drake equation is F sub p, the fraction of stars that have planetary systems. Now here's another famous nebula, the Horsehead Nebula, because it looks like a horse's head. Again, we see the reddish glow. This is excited hydrogen emitting that red color. So there's lots of hydrogen in this nebula. The darker regions, that's the dust. And we learned that this space dust, these are the heavy elements and small particles of material, dust particles and small rocks and chunks of ice, etc. That's the stuff out of which to make rocky planets. So gravity can compress clouds of hydrogen to make stars, and gravity will compress these bits of dust and particles and rock and ice into rocky planets. So nebula have the stuff to make new solar systems, and not just stars, but if there's dust, you can have stars with planets. And back in December of 2020, we had an exciting phenomenon called the conjunction of Jupiter and Saturn. This picture was taken with a very small telescope, and here we see Jupiter and Saturn. You can just barely see the rings of Saturn with this small telescope. As for Jupiter, notice the little spots of light. Those are 4 of Jupiter's moons. This is the kind of thing that Galileo would have seen in using his telescope. And he noticed over successive evenings and successive weeks that these spots appeared to take up different positions. And so he concluded that they were satellites. They were moons of Jupiter. So the question again is, what fraction of stars in our Milky Way galaxy have planets? Now, only 30 years ago or so, that question was unanswered. Scientists could only speculate about that. But in the 1990s, we got the first evidence that a star had a planetary system. Today, scientists estimate that of the hundreds of billions of stars in our Milky Way galaxy, most of them are likely to have planets. So that is a staggering thought. Hundreds of billions of solar systems is what our Milky Way galaxy is. And of course, our beautiful planet Earth might potentially then be just one of an immense number of rocky planets in our Milky Way galaxy. So the next term in the Drake equation is N sub E, which represents the average number of habitable worlds per solar system. Now, we've learned that what scientists mean by a habitable planet is that there's liquid water on the surface of the planet. So that means the planet has to be in a certain orbital zone so that it's not too close, not too far away. It's in the right zone so the temperatures are just right so water can exist as a liquid on the surface of the planet. And of course, our home, our Earth, is characterized by lots of liquid water on the surface of the planet. We have vast oceans, and then on continents we have lakes. Now, habitable worlds do not have to be planets. So if we return to Jupiter and Saturn, although you can't see the moons of Saturn here, but a habitable world might include the moons of a planet. And scientists are very interested in some of the moons of Jupiter and Saturn to see if they might have conditions that might permit various kinds of chemistry to occur and perhaps the conditions for life to emerge. The next term in the Drake equation is F sub L, the fraction of those habitable worlds on which life emerged. Here we see our little icon for the origin of life. Now on Earth, life is cellular. We have encountered various kinds of cells under the microscope. Here we see a picture of bacteria. These were the inventors of life, the simplest type of cells on planet Earth. But then something happened. Some 2 billion years ago, cells got big and complex. Here we see the predatory amoeba attacking its prey, the paramecium. Now, cells are composed of molecules. Here's a cartoon cell over here, and the 4 categories of molecules. We have lipids forming the membrane. We have sugars, a source of energy. We have amino acids, the building blocks of proteins, and then DNA. And of course, it's DNA that stores the recipes for building proteins, which do all the chemistry and all the important jobs inside cells and allow cells to be alive and to maintain their life. So somewhere on planet Earth, some 4 billion years ago, these molecules were being cooked up by some geochemistry, and they assembled into the first cells. So this would be an artist's rendering of the origin of life. So this is a fantastic idea that chemistry produced life. Of course, the time span is immense. We're talking tens to hundreds of millions of years of chemistry producing the needed organic molecules that assembled into the first living cells. Now, of course, DNA is critical for the story of life on Earth, and we mentioned DNA serves one function. It stores the information to build proteins, and proteins are the workers of the cell. They perform the chemistry of life. But importantly, DNA can be duplicated, and this allows living things to reproduce with heredity. So living things can pass on the information to build the all-important proteins. And importantly as well, when DNA is duplicated, sometimes mistakes happen, and these mutations allow for future offspring to vary, to have different characteristics, and so allow populations to undergo evolutionary change. Now, what this means then is that already with the emergence of these simple cellular creatures some 4 billion years ago, the potential existed for animals with big brains to one day ponder their origins. So this simple little life form, if you give it 4 billion years, evidently it can become really complicated animals with really complicated brains capable of inquiring into the deepest nature of our universe. Now, if there are other living beings in our galaxy, if they reproduce, there must be some kind of hereditary system, some molecule or molecules that carry the information for their own construction and then can be used to and passed on to build the future generations. On Earth, it's DNA. On some other planet, perhaps it's some other system, but they must have some molecule or molecules that play a similar role. Now, the next term in the Drake equation then would be the fraction of habitable planets on which life evolves intelligence. So it's not enough that life evolves on the planet. We have to have intelligent life. Now let's use this diagram to situate intelligence in the history of life on Earth. So here's our Drake equation, and we're interested in this transition from living things emerging on a planet to living things becoming intelligent. Well, here's our sun, here's our planet, nice liquid water on the surface, underneath the oceans, perhaps 4 billion years ago, the origin of life. And the earliest life forms were simple cells. We can call them bacteria, and there was another group of cells called archaea. And this is what ruled the planet for around 2 billion years. It was just tiny, single-celled organisms. But then something happened around 2 billion years ago. A member of each of these groups united to form something more complex, and evidently it was a very successful union. But this was an important event. This was an endosymbiosis event, and this set the stage for the evolution of all life forms more complicated than bacteria. And of course, on Earth, all intelligent organisms are composed of these large complex cells. And so this event here is what set the stage for the evolution of intelligence on our planet. Now here we see a more complicated diagram showing the history of life on Earth. Down here, bottom left, we have the origin of life, and then we have a long period of time where bacteria were evolving different characteristics, and then we get this merging of two cells. One cell got inside another cell. This is the endosymbiosis event. It's the origin of mitochondria. Now cells had lots of energy. They could get bigger. They could support larger genomes. And these single-celled organisms were the ancestors to all future complex life on Earth. And if we follow this path down here, cells stuck together, forming the first animal colonies, and animals evolved, some of which evolved backbones, and the vertebrates then colonized land, and of course then it's a couple of vertebrates today that we associate with intelligence. On our tree of life, of course, we have the origin of life at the bottom, and then here's that critical endosymbiosis event forming large complex cells. And then we have multicellular animals, and here's the animal branch on the tree of life. Well, the organisms that we associate with intelligence, humans of course, and maybe, the apes and perhaps some whales and dolphins and things, well, there are just a few species on this animal branch that are associated with intelligence. But none of these intelligent species would have existed were it not for that symbiosis event. Of course, it is our species that shines with respect to the size of our brains. Our brains got very big. Now, why was that? Scientists suspect that the key to our success, the key to the success of our human ancestors, was culture. That we were the species that was extremely capable of acquiring culture and transmitting culture. And so natural selection then would favor brains capable of learning from others in our group and making improvements on the way we do things, and then transmitting that cultural knowledge to our offspring. So our species is characterized by a prolonged period of childhood, and everywhere in every human group, children grow through an extended period of cultural learning. So when we're born, our baby brains have all the neurons we're going to have. It's just that the neurons don't make extensive connections yet at this time. But cultural learning is going to create a more complicated set of patterns, of networks, and that will embody all of the knowledge and skills that we're learning in our culture. So this process of learning culture and then using culture and generating new culture. That was the key to our ancestors' success, and that set up selection pressures for larger brains over time. And so today we enjoy a large cerebral cortex capable of learning lots of information, storing information, and we can use that information in flexible ways, and that makes us a very, very impressive intelligent species indeed. The next term in the Drake equation is F sub c, the fraction of habitable worlds on which communicating technology develops. You'll notice the icon here is a radio dish here. So we're talking about technology that manipulates electromagnetic waves. We're not talking about the wheel or the printing press. We need to focus on the technologies that could be used to communicate across the vast distances of our galaxy. Here we see a couple of pictures again of our Milky Way, but this is a radio telescope in Owens Valley, California. Here's another picture of that. And here we're at the McDonald Observatory in Texas, near Fort Davis, Texas. And again, a radio telescope here, and then optical telescopes as well. So it's these instruments that scientists can use to detect radio waves coming from the universe, but also they could be used to transmit radio waves as well. The final term in the Drake equation is the L, average lifespan of a communicating civilization. Now here I made a little icon here that for our civilization to have a long life, we need to be able to live with our technology. But there are challenges. Our technology can pose challenges. We have weapons, for example, that could potentially destroy our species. Our technology might be polluting the environment in ways that make future life unsustainable. Perhaps the artificial intelligence will be a future threat to us. On the other hand, other technologies might allow us to colonize other planets like Mars, and that will give us maybe an insurance policy in case we mess up Earth. But the idea here is L captures how long is a technological civilization going to last? What's the average lifespan of such a civilization? And that's important for the following reason. Take a look at this picture here. Here's a representation of our Milky Way galaxy. And if you can see this little blue dot here, that little blue dot would be centered on our Earth. Let's magnify it right here. That little blue dot, the extent of that blue dot is how far our radio and TV signals have gone out into our galaxy. So our transmissions traveling at the speed of light have only reached just the nearest neighboring star systems in our galaxy. And so this is one of the sobering things. The extent of our Milky Way galaxy, it's immense. It would take about 100,000 years for light to travel across the diameter of the galaxy. So this means that even if a civilization has communicating technology, they're going to have to be around for a long, long time for their messages to get very far into the galaxy, and then let alone to receive a signal from some other intelligent civilization. All right, so that's the Drake equation. We're estimating how many communicating civilizations, and when we multiply rate of star formation, fraction of stars with planets, the number of habitable planets in a system, fraction of those habitable worlds where life emerges, fraction of those worlds where intelligent life emerges, fraction of those worlds where the life gets intelligent enough to make technologies that can be used to communicate across the vast distances of the galaxy, times the average lifespan of the civilization. You multiply all those terms together and you get a number. Well, so what is the number? What's this value? Of course, that depends on the values you put in for these terms. And you can do a Google search or an internet search and find out how different astronomers and different cosmologists and different biologists and astrobiologists might sort of plug in numbers for these terms. So I'm not going to give values for these terms right now. Scientists are reasonably confident in the values for the first three terms. But that's not the case for the last four terms. And so in the final lesson, we'll go into more detail about these four terms. And it may well be that one or several or all of them are small. And if they are small, that will correspondingly reduce the value for n. And disappointingly, that might explain why it is that we have yet to detect the presence of any other intelligent communicating civilization. I mean, after all, right? Where is everyone? There are so many stars in our galaxy and so many habitable planets orbiting those stars. Are we the only ones in our galaxy? So in the next lesson, we'll dig a little deeper into those last four terms.